All right, good morning. And today what we want to do is we want to pick up kind of where we left off. We left off looking at different applications of Ampere's law. And so I'm going to go back and review a couple of these slides. Remember, Ampere's law was this theorem which allowed us to calculate magnetic fields using symmetry of a particular situation. And Ampere's law is based on this idea. You can start from the equations that we've shown for magnetic fields and how magnetic fields are generated from moving charges. So I guess that's the first thing we really want to re-emphasize, is that anytime I have charges in motion, either with a velocity or an acceleration, that's going to generate a magnetic field. So far, we've specifically been looking at magnetic fields that depend on the velocity of charges and what those formulas look like. We said in future chapters we will be introducing electric and magnetic fields that are related to accelerations of the charges. So the charges are the basis for all of this. Now, a current is a bunch of charges in motion. So a current is already not looking at individual point charges, but it's looking at a whole collection of charges all moving in some direction. And we can start from the basic formulas for calculating magnetic fields, and we can derive this theorem called Ampere's law. Ampere's law says this. It says if we carry out a path integration of the magnetic field, that the path integration is always proportional to the amount of current running through that region. And we said this is kind of like Gauss's law. Gauss's law said that if we enclose a bunch of charge, integrating the electric field over that enclosed volume is proportional to how much charge is inside. Before, with Gauss's law, it was a surface area we were integrating, and now we're going to integrate along a path. So we're going to use a path symbol of dl or ds to represent that integration. Now, the example they've given here is kind of zigzag, and we said that's to emphasize the generality of this theorem. It says it doesn't matter what path we take. By the time we have completed a closed path, keeping track of the B fields all the way around a current, that Ampere's law will work. Now, we said it's not really useful when we have crazy integration paths like this. It's the symmetric integration paths that are useful. So what we're looking at here is we've now decided to take a perfectly circular path, and for that circular path, what we can say is this integration that we started off with, which looked a little terrifying, actually reduces down to the B field times the length of the path all the way around. And that can be set equal to the current, and that gives us the magnetic field formula that we've been working from that says how much magnetic field will we have surrounding a wire with a bunch of current in it. And then this was my own drawing of that. Now, instead of using the mu naught, which the textbook is using, I'm going to stick with 4 pi k over c squared. And again, here is the path integration. B times the length of the path, the circumference here, is 2 pi r. And we can set that equal to the enclosed current. And then this became the formula for the magnetic field surrounding the wire. Magnetic field depending on how much current and how far we are away from the wire. And then we looked at an example, a more complicated example. We said, okay, we've used Ampere's law to come up with a function for what does the magnetic field look like outside the wire. What's the magnetic field like inside the wire? How would that be different? And the difference would come from using a path that actually runs through the wire itself. So we've taken that copper wire, for example, and we've blown that up so we can actually look inside the wire, draw our circular path, and carry out a calculation for the magnetic field. So here it is. Now what we did is kind of side-by-side comparison. We said here is Ampere's law being used for locations outside the wire, and we get the same formula as before by taking the magnetic field times the path length is equal to 4 pi k over c squared times the enclosed charge. It leads to that formula. Now we want to look inside the copper itself. And for that, we're going to say, well, now I'm looking at a path that's within the wire. Big R is representing the radius of the wire itself. The left side integration turns out to be the very same thing. I'm still getting B times 2 pi R. But what we said was, since we're following a path inside the wire, we're not going to have as much current. The assumption here is that the current is uniformly distributed across this cross-sectional area, and that meant that we only wanted to use the fraction of the current enclosed by that path. And the area of that, or that fraction, is the area within the path compared with the total cross-sectional area, and that ends up introducing this, this ratio. So when we carried out the calculations using that, that gave us a formula that behaved like, it was linear, and what it told us was, well, right at the center the magnetic field is 0. Well, that makes sense. If I get right to the center point of the wire, there's enough symmetry there to argue that the B field can't be anything other than 0. And then it specifically predicts that the magnetic field rises linearly as we make our way from the center of the wire out to the surface of the wire. And then once we leave the surface of the wire and head away from the wire, it's going to drop off according to this formula. So inside the wire, we have linear R behavior in the function. Outside the wire, we have the 1 over R asymptotically dropping off magnetic field behavior. So both coming from Ampere's law. Now again, Ampere's law is assuming that there's a lot of symmetry, and we really only have the symmetry there. Let me stay on this one for a, maybe come back to here. We really only have the symmetry, we can only argue that, if the wire is really long. Now, we've been drawing certain sections of wire, but when you think about wire, the wire can't really stop. If I've got current moving through the wire is part of a complete circuit. Now what that would say is, sure, the wire runs straight for a while, but at some point it's got to curve around and complete the circuit, and that breaks the symmetry that we're assuming for Ampere's law. So again, it's an approximation. As long as we stay relatively close to the wire, compared with what its length is, it's going to be a very good approximation. Now, we can also ask this question, well, sure, this is the magnetic field, that's really interesting. Why isn't there an electric field also? Now, the electrons in the wire are in motion, the protons are not. So the protons and the electrons, their electric charge, cancels out. And that pretty much does away with the electric field. So what makes wires, running current through wires, so interesting or useful for us, it's a way to create magnetic fields with minimum electric fields. The electric fields that we're generating are basically 0. And so that's why the wiring becomes such a useful way of thinking about generating magnetic effects. So we can use currents in wires to generate magnetic force on other wires with current in them. I can get wires, and I can bend it however I want, and I can get interactions between different currents acting in different parts of a circuit. An electric motor, for example. All right. Let's look at a couple of other kind of useful examples using Ampere's law. It does turn out that this is a very handy way to solve for magnetic fields in some of the most common situations that we have. So let's try a coaxial cable. Now, a coaxial cable is this. You know, in a lot of appliances, when we plug those in and we look at the wiring, you can actually see the wires side by side. So those two wires combined are completing a circuit. Now, if I put wires side by side, there's going to be a leftover magnetic field outside of them. That leftover magnetic field could influence other wires. It could have an effect. There could be crosstalk between these wires and another set of wires nearby. A solution to that is that rather than having the two conductors, you know, the two wires side by side, what if we place one of the wires inside the other one? So that's what a coaxial cable does. It has one wire, one conductor, a circular wire running through the center. That's surrounded by a sleeve that's insulating. And then there's a second cylindrical shell, you can see how that's been wrapped here, of conducting material. Now what that does for us is imagine drawing a path all the way around this wire to determine what the magnetic field would be. And in this case, Ampere's law tells us that if I draw a circle outside of a coax, the symmetry argues that the magnetic field is going to be the same value at all locations. And the symmetry is present because of the way we've nested one wire inside of the other one. So that says that the magnetic field outside is going to be uniform along a circular path, and that the total current running through it is zero. So the total current, the included current, is zero because we've got one conductor carrying current I in one direction and this cylindrical conductor carrying an equal amount of current in the opposite direction. Ampere's law says that's a pretty symmetric situation. The magnetic field will be the same at every location and it's going to be zero. So that says that a coax cable, to a large degree, as long as it's running straight, is going to cancel out all these magnetic effects. And that means that, you know, if we're running a signal through one of these wires, it won't have an effect on a wire sitting right next to it. You can run a bunch of these coax cables near each other, and they won't generate magnetic fields that disrupt the other wires. And Ampere's law is a good way to, you know, draw the diagram and say, oh yeah, using Ampere's law we can see, using this theorem, that the magnetic field should cancel out outside. Now within the insulator, this is asking about that, within the insulator you will have a magnetic field due to the presence of the current inside. If I draw not a Gaussian surface, but an Amperian path, if I draw a magnetic field path in there, well, yeah, there is going to be a net current, and there will be a magnetic field. So there's a magnetic field between the two conductors, but once I get outside of that outer conductor, the magnetic field is gone. So a really handy setup, really handy geometry. Coax cables are used a lot in, well, anytime you don't want crosstalk. Musical cables are typically, cables between amplifiers and speakers, for example, are typically coax with the idea, or often coax, with the idea of minimizing the crosstalk. All right, let's move on and look at a different example. Now, this example is this. So this is actually kind of hard to see. I don't know if you ever saw any of these just lying around in the lab room, but I went online and looked for a solenoid. These are called solenoids, and we're going to find out they have some really useful, interesting properties to them. What they are is they're a coil of wire. Now, up until now, we looked at coils of wire that were kind of flat. 10 loops or so, and they all were kind of compacted. This, it's hard to tell from the way that the photograph worked. The wiring is actually looping around those cylinders. Now, the ones we have in lab have like 540, something like that, loops. And then we got another set in our lab that have like 3,000 and something, 3,200 loops, something like that, of windings around these solenoids. So again, they have useful properties. We can use these actually to generate magnetic fields. So this gives us, by taking a bunch of wires and wrapping it in a series of loops very compactly, we generate very large magnetic fields on the inside of these solenoids. So if we go back and take a look, here is a cut open view of what the solenoid looks like. So if we cut that solenoid kind of along its length, what we've got then is all these loops of wire wrapped around. So here is the wiring, this time it's the current. A loop comes around, and then it goes back in, and then it comes back out, and it goes back in, and it comes back out and goes back in. What that will do is it'll generate a magnetic field, a very large magnetic field concentrated within the volume of the solenoid. And you can see these are our current designations. So, that's a diagram worth staring at for a bit. Now for this, we can use Ampe's law. The path is a little different this time. Let me just take a look at the next slide and see what I've got here. Yeah, I may be going back and forth from these a bit. Let's see. I could pick, for Ampe's law, I could pick a path that follows the magnetic field inside, and then at some point, I could turn and go perpendicular. And then I'll follow a path outside the solenoid, and then again I'll turn and go perpendicular. Now there's some assumptions we make here. So the formula we end up with using Ampere's law, it's an approximation. It's not an exact formula, but it's a pretty good approximation. In fact, in future labs we'll probably see that. And we'll see how that works. We'll set up some video labs. We'll send out some instructions for the labs. You guys can individually, wherever you're sheltering in place, you guys can individually collect different items from around the house. And anyway, we'll see how that works. So we're going to follow a path here. Turn perpendicular again. Now, remember, Ampe's law says it doesn't matter what path we pick. And at first, when I look at this path, I'm thinking, I don't see the symmetry. How am I actually going to carry out the calculations here? And where the symmetry is this. If we have a really long solenoid, then certainly, at least in the central regions of that solenoid, the magnetic field is going to be roughly uniform. So the magnetic field needs to have the same value, because when I stand inside the solenoid, I can't tell, if I can't see the light at the end of the tunnel. So I'm inside this circular solenoid and I look, and it just seems to go on forever in both directions. Then as I wander around in that central region, I go, well, if my environment looks the same in all directions, I must be in a region of uniform magnetic field. So what we do is we integrate this path where we have a uniform magnetic field. Now here we turn and go perpendicular. If you remember, Ampere's law requires us to keep track of not just the magnetic field, but the magnetic field components specifically along the path we're integrating. So if I turn and go perpendicular to the magnetic field, that's not making any contribution to that path integration. The path integration contribution goes to 0 for these perpendicular directions. Now, there is a path outside of the solenoid But the assumption we make here is because of the way the wiring reinforces the magnetic field in the central region, what we do is we assume that the magnetic field outside the solenoid is negligible compared with the magnetic field inside. So here's our path. It's a rectangle. Magnetic field is large and uniform inside. It goes to 0 on the sides here, and then for completing the path in the outside region, we just say it's so small we're not going to pay attention to it. What that turns into, using Ampere's law, is this. So here's the solenoid that I've drawn, and I wanted to step back away from that and say, well, what happens to the magnetic field lines once you leave that? The magnetic field lines always loop. They always close on themselves. So if I've got a bunch of magnetic field lines passing through the solenoid, those lines can't just stop at the end. They're going to loop back around and complete closed loops. Now, these loops outside are less concentrated, and that says that the magnetic field outside will be much lower. So the path that we're going to integrate looks something like this. I didn't draw this so well. This could, we may have to go back to the other slide to take a look at it. So here's the magnetic field uniform, and then I'm going to turn, and then I'm going to follow this path. You can kind of see it here in some dashed lines. And that says that when we carry out Ampere's law, so I've got it written down here, let's think of the left side here. The magnetic field is integrated along a length of L. Now I use big L instead of little l because I feel like that's easier to see for board work. In any case, that's what this one path corresponds to. And then all the other paths, we said we're just going to assume are 0. So integrating along the closed path leaves me with b times the length of the path, and I can set that equal to 4 pi k c squared times the enclosed charge. Now notice that when I take that path, the path integration for Ampe's law, I'm enclosing the current many times, not just once. So if I've got a solenoid, which is what these are called, so I have a solenoid here, it's got n number of loops. Then if I look at the path that I've defined, the path goes through it n times. Let's go back and look at, I have to say this is a nice clean looking one. Let's go back and look at this. What I'm going to say is here is the end of the solenoid. See where the current stops. Instead of limiting ourselves to this path right here, what we can do is we can extend it right out to the edges. It turns out it doesn't make a difference in the formula. And it's a little easier conceptually to think about that. So if I extend little l, so it's the full length of the solenoid, then what I can do is I can include all of the loops of wire. So if I get n loops of wire and the full length is little l, what that leads to is this formula. Now maybe I should apologize for using big L. But they're using little l, but that's the formula. And it's an estimate. And we assume that that formula is a pretty good representation of the magnetic field everywhere inside the solenoid. Now in reality, it really is only a good representation of the B field kind of in the central regions. If I get close to the edges, the magnetic fields are already going to be dropping off as I get into those regions. So that's a formula, though, that we'll be using. Again, we'll be looking at some of this stuff in labs, measuring magnetic field effects with solenoids. All right, now there is there's a calculation here. I didn't set up. I didn't go through the calculations in here, but what it's saying is that there's a solenoid. We're trying to calculate the field inside. It says that the solenoid is 10 centimeters long, and it has 400 turns, and it carries a current of 2 amps. Calculate the field inside. So that's the numbers that are given. And I think, you know, we've done the integration. We've used Amps law. We came up with this formula. So now we plug the numbers in. If N is equal to 400 and L is equal to 0.1 meters, and what was the value on the current? 2 amps. So you should be able to see, going back and forth here, we have all the numbers that we would need to plug into our formula. We can plug numbers into that formula, and we can figure out how large the magnetic field is. So I should have thrown those numbers in to get a number, but I did not do that on this example. I will leave that for you guys to take a look at. Now, another shape for a solenoid that we could use, instead of using a solenoid, which we think of as just being straight, we could use a torus solenoid or a toroid. So a torus, also known as a donut, is a solenoid which has been closed at the ends. So rather than, again, just having a solenoid, we make a torus-shaped solenoid, and we call it a toroid. And those are the paths that we would use. So there's a path out here that says what's the magnetic field outside the toroid, and that path integrates to 0. So for a toroid, Ampere's law predicts that we'll get 0 magnetic field outside of the toroid. And there's no assumption really made here. So for a perfect toroid, I guess that's the assumption here, is that the current is uniform. The wires are spaced so closely together, it's as if there's a sheet of current wrapped around the donut. If that's the case, then there's no magnetic field in these outer regions, and inside the toroid, we can calculate the path length, which would be the magnetic field times 2 pi r. And then we can set that equal to however many loops of current we have traveling through. So, so you can also take a look at this, derive a formula for the toroid. Nice feature again is we're not making assumptions. There's no edge effects because we've closed the ends off by wrapping them together. Okay, so that's a good example also to take a look at. So we've looked at Ampere's law, and we said Ampere's law is really handy. It's this high-level theorem that lets us integrate a path and use that to calculate a magnetic field when there's a lot of symmetry. What if there's not a lot of symmetry? What if Ampere's law is not providing a simple way to go in and determine magnetic fields? Well, then we can come back to kind of the basic brute force method, and that's known as the Biot-Savart law, the BS law. Gives us the magnetic field due to an infinitesimal length of current. So we'll switch back and forth. Here's their diagram. I've got a diagram in here too. And so as current travels along, I can break that current down. Let's try looking at this. So let's go back. We've looked at this diagram a couple times now. Once when we started out chapter 27. We're bringing it back, and we looked at it earlier in chapter 28. We're going to bring it back one more time and say, you know, the real basis for these magnetic fields are charges that are in motion. And we had written this formula down, said this is kind of our starting point. So the magnetic field depends on how much charge we've got, which is Q. It drops off with distance, like 1 over r squared. And then it depends on how fast the charge is going. That's the V over C. And then finally we said that there is this cross product we have to keep track of, and that cross product gives us a factor of sine theta. So just as a reminder, so if the charge is headed in this direction, then if I'm looking out, let's say point A, and that's at a distance of r, which we could write in right there, and at an angle theta, then we showed, carrying out the cross product, the magnitude of the magnetic field, that's an equal sign, is kq over c squared, v over r squared times sine theta. Now, again, we had a factor of c up here to make sure that the magnetic field components are kind of on an equal footing with the electric field components. But for a formula to use within the chapter, we carried that extra factor of c over. So that gave us two factors of c. We still have the kq over r squared, but we have a factor of v and a factor of sine theta. Now, what we would like to do is start with our formula for the magnetic field due to a point charge in motion, and use that to represent a whole series of charges, not just one charge, but a whole series of charges that are all in motion. That sounds a lot like a current. So what we're saying here is I have a wire, there is current moving through the wire, and what we can do is say that the current consists of a whole bunch of short sections of dqs. So there's a dq right there. See that length ds? If I break up the current into a bunch of little infinitesimal current segments, each with length ds, each one of those ds's contains a charge dq. And each one of those dq's is moving with velocity v. So we're going to try a trick now with the notation. What we're going to say is, look, if every little bit of charge moving with velocity v is generating a little bit of magnetic field at that location right there, let's take that little bit of charge moving at velocity v. Now, the v can be written as dx dt, or probably for this example, we want to write it as ds dt. So I've taken dq times v. The dq is there, the velocity is dx dt or ds dt. Now what I'm going to do is think of moving the dt over to the dq. Well, that turns it into current. So what we've shown then is that a little bit of charge moving at velocity v, that's becoming a source of a little bit of magnetic field. We can now pull out the dq times v and replace it with its equivalent, which is I times ds. So a little segment of wire length with current moving through it is equivalent to a little bit of charge moving at some velocity. And so I've gone from this formula, which was based on the idea of charge in motion, to this formula, which is based on a short segment, ds, of current. Now, I can now build up a formula for the magnetic field due to a current by integrating a bunch of all these dBs. And what I'm going to get is, well, all the constants can stay outside the integration. I'll get Ki over c squared. And then what stays inside the integration is there's a factor of ds over r squared, and that factor of sine theta could also be varying. So if I'm following a wire with current, well, the current's going to stay constant at all locations within that wire. K over c squared, those are both constants. So the stuff that has to get integrated is the short segments of ds, the distance for each of those, and the angle. Now, right below it, I went back and I said, what if I continued thinking about this in terms of charge, not so much in terms of current? What would the formula look like? And that's it. So two optional ways I'm going to call this our brute force, systematic, start from the ground up approach to calculate a magnetic field. So these formulas will work for any distribution of current, any distribution of charge, and they can be used to calculate exact formulas for the magnetic fields. The question always becomes, how difficult is it going to be to carry out these integrations? And we'll look at a couple of examples where it's doable. But in general, these could become more complicated sorts of calculations to carry out. So again, the text is calling this the Biot-Savart law. That's kind of the name it goes by. Let's take a look at their diagram, which looks pretty nice. So here is a wire going along. Here is some reference point that they've picked here. And what they've got is they're picking a point P out here where they want to measure the magnetic field. Now, the first thing I want to do is I want to get the direction figured out. So the direction on this, let's go back and look at our setup. The direction should be the direction of velocity crossed with the radial direction. So keep this in mind, and we'll jump back ahead to their slide. All right, where are those two unit vectors? I know they disappear when you go to the next slide. Where are those two unit vectors? Well, I'm thinking of this short segment right here, ds, or dl, or dy, whatever we want to designate as. If I now head out towards that point, well, the radial unit vector is pointing away from the source. So it's pointing in that direction. What direction would the velocity unit vector be in? So I've got a radial unit vector here. The velocity is in the direction of the current. So the velocity will be right along the wire. I know the electrons are going the opposite direction, but when we look at current, we're thinking of that as positive charge moving in the direction of the current. And we said that for these problems, it'll give us the same answer. So I'm going to think of velocity as the direction that the current is traveling in, and radial is radial. So when I look at that point there, what I've got is I've got a radial unit vector here and a velocity unit vector here. Again, going back to that formula. All right. So for this diagram, what I want to do is I want to do velocity cross radial. So velocity is here, radial is there, and if I do a cross product, its cross product is into the board. And that's what they've drawn. They're saying that that little bit of magnetic field right here being generated by that short section of current, that magnetic field is going into the board. Now, how is that going to change when I move from one of these locations to the next? And what happens is the velocity vector never changes. The velocity vector continues to be along that straight path of the current, and so at that location I'm getting a velocity vector that's always here. That unit velocity vector is lined up, so it's telling us the direction of the current that's generating the magnetic field. Now the radial unit vector is going to change. So the radial unit vector will gradually change angle as we move to different locations. So you can kind of see, again, let's go back and write down, take a look at the formula. You can see how carrying out these integrations, they could get to be complicated. The angles could be changing, the distances could be changing, the ds may have to be maybe following a curved path or something. All right, let's try an actual calculation. We didn't do the straight wire. We could have. That straight wire actually gives us a formula that matches up with what we've already solved. using Ampere's law. So let's use a different example. The example we're at now is a current loop. So this is a circular path of current. The current is coming out here, curves around and goes back in. So that's what the O and the X's are keeping track of here. But remember, it's a complete ring. This ring has a radius of R to it. So that's a fixed value that we're going to work from. And then here is a point right along the axis. So I've got a ring of current like this. It's kind of like one loop off of a solenoid, right? So the solenoid had many, many loops to it. This is the magnetic field due to just one of those loops inside one of those solenoids that we took a look at. So if we can calculate this, that'll give us a starting point for calculating the magnetic field of a solenoid using this approach, which we're not going to do. But we're just going to look at this one ring of current, that's all. So if I pick a point on the axis, and I'll say that's a distance x away from the center point of the ring, well, if I do that, then where is the velocity vector and where is the radial vector? Where are my unit vectors going to be? Now, the radial unit vector is going to be here. That's the direction pointing away from the source of the magnetic field. The velocity vector is going to be the direction of current. And remember, this particular location we're looking at, the current is coming out of the board, so that's the velocity direction. So the velocity direction is coming out of the board. It's got to match up with that, it's got a parallel transport from that location. And then the R is here. So the R is here, V is coming out of the board, and when I look at those two vectors, those are perpendicular to each other, okay? And their cross product is going to be tipped at an angle as shown in the diagram. Now in the diagram here, they've used angle phi for this and angle phi here. Let me flip ahead to my notation here. I've used a different angle. I chose to use this angle, it's complement, so I'm using theta, and that says theta is here on the diagram. I've also tried to be really clear about writing in, that's the direction of the radial unit vector. There's a little bit of current right there, ds, and I've also drawn a second picture here. So I've kind of flipped the loop a little bit, just enough, so you can see where the ds is located. That ds is coming down. There is the radial unit vector. Here is the velocity unit vector. There's that little bit of magnetic field, and then I've broken that up into components, cosine and sine. Okay, but strictly speaking, the loop of wire is in this plane. There's a central axis leading out to point A. There is my magnetic field. There is the sine theta component. There is the cosine theta component. What's left to do now is integrate along the circular path of the current itself. So I pulled out, this is the Biot-Savart law. Here's my electromagnetic force constant K. Here's C squared. There is the current traveling through this loop. Where are the DS's? And since it's a circular path, I'm going to have a whole series of DS's that lead me around in a circle. So the DS designation is nice. It's not along the X direction, it's not along the Y direction, it's varying as I go around that circular path. And then what's happening with R? R is going to be the distance from each individual segment of current out to the point. And since we're on the axis, R actually is a constant in this example. So the general solution here that we want to solve is this, but what we're finding is R is a constant. What about Okay, now there's two angles going on here. This is the angle from the cross product, and so that's at 90 degrees, that goes away. Here is the angle from the picture, and that's what I'm going to use to keep track of the sine and cosine components. Now, which component do I want to keep? Do I want to keep them both? Or is one of those going to cancel out? And as we integrate along that ring, what's going to happen is all of my lateral components will cancel out with each other. The lateral components are going to, as I integrate around, they're going to go in all different directions, and a vector integrated so that it goes equally in all directions is going to cancel out to zero. So I can ignore the cosine theta component. So that tells me this: to get the total magnetic field, I'm going to integrate this component, the one right along the axis, and that also tells me what direction the magnetic field would be in. So the magnetic field is going to be oriented right along the axis, and its magnitude is going to come from adding all of those dB sine thetas together. So this part from the cross product, the factor of sine phi from the cross product goes away. That's not the same phi as what they used. I apologize for that. But the sine theta from this diagram is going to stay around. So this goes away, the sine theta stays around. Now as far as r, the r value that we have here, the distance, that's going to be x squared plus r squared, where big R, here it is, big R is the distance from the center of the ring out to the circumference, out to where the current is actually running. All right, so I've got the R expression in terms of these guys. Now the sine theta, when I look at this diagram, sine theta is going to be big R divided by hypotenuse, which is little r. So I can substitute that in also. Now little r, again, is going to be given by x squared plus r squared. So once I've got all those pieces taken care of in this integration, what I'm left with then is the little r's come outside, the big R factor comes outside, the sine phi went to 1, the sine theta was replaced with the r's and the little r's. The only thing left in this particular integration, this one was, and we said we were only going to look at one or two examples where the integration is reasonably straightforward. I realize setting everything up, there's a lot of conceptual stuff to think about here. The only thing left in the integration sign is just ds. It turns out that since every short current segment is contributing equally to the value of dB, that everything drops out except the ds. Now, integrating together a bunch of ds's would just be the total length all the way around that circular path. So the final result I'm ending up with here, k times I over c squared, I've got one factor of big R. In the denominator, I have 3 of these factors. I've got 2 factors of little r here, one more coming in from sine theta, and that leaves me with x squared plus r squared to the 3/2. And then integrating all the way around, integrating ds all the way around, is giving me an additional factor of 2 pi r. So that's the formula that we have is right there. And now what we can do is we can ask what happens in a couple of different locations. What would the magnetic field look like right at the center of the ring? So if I have one loop and I'm looking at the magnetic field right at the center, the first thing to realize is I'm going to get a magnetic field that's pointing in that direction. Now that might seem like, why am I getting a magnetic field here? You know, I look along this central axis, and I've got a magnetic field that's pointing along a particular direction, isn't there a way I could change the direction of the magnetic field? And what would that take? And so changing the direction of the magnetic field for this example, what I could do is reverse the current direction. So with the current going this way, the magnetic field lines are passing off in this direction through that loop. If I now reverse the direction of current, then I'll reverse all the magnetic field directions. I'll now have a magnetic field passing back the other direction through that loop. If we do pick the center of the ring, we can set x equal to 0. Setting x equal to 0 in that formula, I'm going to get a bunch of cancellations with the r's, and it leaves us with 2 pi ki over c squared times r. So that's a formula that we're ending up with, and that formula is the magnetic field at the center of the ring. Okay. Here's another example that we could imagine taking a look at. Here we have a wire carrying current. Here comes the wire carrying current to this location, and then what happens is we turn and we follow this curved path, and then we turn again at 90 degrees and the wire heads off. And the current follows the wire. So we've got a bunch of current inside the wire following that particular path. And what we could ask is this. We could say, okay, fine. As far as point C, which is at the center of that circular arc, that 90 degree or 1/2 pi circular arc, current coming in this direction, if there's a point right out in front of those charges, that's going to be 0. There's not going to be any contribution to the magnetic field at that location, because that's right along the direction that the charge is headed. So I can ignore the effects from this part of the current. What about this part of the current? Well, it's the same argument. If we go back and look at our general diagram for this, what it says is if I have current headed in a particular direction where theta is equal, if I'm looking at a point right in front, theta is equal to 0, and theta equal to 0 says I don't have any magnetic field in that direction. As long as it's right in front or right behind the current, that's not going to generate any magnetic field either. So what we're down to is this. What we're down to is this circular path. And the setup for this circular path is going to be pretty similar to what we just looked at. In fact, let's go back and ask, how could we take this diagram that we set up, and instead of a ring, what if we simplify it down to a point right at the center of the ring? Well, if we take it right down to a point at the center of the ring, then we're going to be back to this formula that we came up with. Now, the formula that we came up with had us integrating all the way around the ring. So that was a 2 pi r integration. In this next example that we've been looking at, we don't do the full ring, we only do 1/4 of it. So only 1/4 of the ring would give us 1/4 of this value that we've calculated for the center of the ring. So, and let's take a look at that a bit too. So there it is, there's the 1/4 of the ring. And that's what we're going to end up with. So we're going to end up carrying out a very similar integration to the example from before in order to determine the magnetic field at that point. Questions on any of that? Okay, so here is this formula for calculating magnetic fields independent, well, for any charge distribution, let's say that. For any charge distribution and in motion, and charges in motion, a good example of that would be a current in a wire. All right, let's pick up this last topic in the chapter. So at the end of chapter 28, a quick review, chapter 28 has been about how do we generate magnetic fields, and the bottom line has been, if I want to generate a magnetic field, I need some charges, and I need them to be in motion. They either need to have some sort of velocity or some sort of acceleration to them. As long as there's a velocity or an acceleration taking place, the charges will be generating magnetic fields. All right, now we started out the chapter looking at magnets, and at that time we said, you know, when people say, oh, magnetic forces, isn't a magnet the simplest example of that? And at this point I'm saying no. Magnets are more complicated. The simplest example is to have a charge in motion, and maybe the next simplest example is to have a current traveling along as a source for a magnetic field. So let's look at magnets a little bit more and ask what's going on. With ferromagnetic materials, now it's called ferromagnetism. It's a quantum effect that takes place in iron, in nickel, a few other materials. And it has to do with whether or not the spins of electrons in one region become correlated with spins of the electron in other regions. As long as the spins on the electron stay random, so that there are no regions trying to align with other regions, then we don't see this effect. And they list iron and nickel as two of the common materials that create this effect. Now, in these materials, what happens is we have what are called domains within the iron or within the nickel material, within the material that's ferromagnetic. The domains are randomly oriented. So what we have is locally, there are regions of the iron where the electron spins are aligning with each other, and that means their magnetic effects are aligning, and they're being reinforced in that particular direction. But as long as the different domains remain random, then we won't have a magnetic effect overall for the material. But what happens is when we place a piece of iron, for example, in a magnetic field, the domains begin lining up with that magnetic field, and the iron becomes magnetized. Now what happens is if we change the external magnetic field, the iron follows. So for just a standard piece of iron, it can be magnetized in whatever direction the surrounding magnetic field is. So this is kind of an interesting effect that the iron takes on and reinforces whatever magnetic field is surrounded. So let's go back to that solenoid as an example. If you remember with the solenoids, solenoids were an example of where we had many wires generating a magnetic field. What we can do with a solenoid is we can take a bar of iron and place it inside the solenoid. By placing a bar of iron inside the solenoid, the individual domains within that iron tend to line up with the external magnetic field that we're producing. So again, it's not 100% alignment, but what we do is we get the iron itself becomes magnetized. So you put a piece of iron, an iron bar through this solenoid, the magnetic field could go up by 40, 60, 100 times because of the presence of that iron. So we can generate magnetic fields using solenoids. We can make those magnetic fields much, much larger just by putting a block of iron through the magnetic field region. So we can use that as, we can use a piece of iron to create larger magnetic effects. We want to keep that in mind when we get into circuits, things like building transformers. That will become important for us. All right, so let's move on and let's come up with kind of a summary of what we've done here. In Chapter 8, we've been looking at generating magnetic fields. Now, what the textbook is claiming is, well, I don't know if they're claiming this, but they're starting off by looking at a straight line of current and saying the magnetic field near a long straight wire is given by this formula. And along the way, we've derived that formula a couple different ways. But I still want to go back and say, take a look at those early diagrams we drew for just individual charges. So individual charges generate magnetic fields. Make sure you're looking at those formulas for individual charges. Now, we said that there's this theorem, Ampere's law, that provides a way to solve for magnetic fields if we're fortunate enough to have a lot of symmetry in the charges and in the way that the charges are moving. So examples for that were long straight wires. That turned out to be a pretty good example. One of the examples with Ampere's law that doesn't work very well. It's easy to get kind of confused, I guess, with some of these examples. I think there's a lot to take in here. So I do think these, these chapters, 27, 28, maybe 28 especially, maybe one of the most challenging chapters that we look at in the course. There's a lot of stuff to take in. When people see the symmetry of a loop of wire, often there's kind of this feeling that, well, can I use Ampere's law somewhere here? But if we take a look at the path that we would need in order to calculate a magnetic field, the path that we would want to integrate along, there's no obvious path that would have enough symmetry that we'd be able to tell exactly what the magnetic field would be. So even though there is a good amount of symmetry to the current distribution, there's not an easy path that we can find that shares that sort of symmetry. So this is not a good example for using Ampe's law. The long straight wire works well, the solenoid works well, the donut-shaped solenoid, the torus, works well. But those are our major examples of using Gauss's law, of using Ampere's law, not Gauss's law. All right. Oh, that was the slide we were on before. Here's the magnetic field inside a solenoid. So we went through and used Ampere's law to come up with that. And we are going to be using a lot of solenoids in future chapters. So make sure you're familiar with the solenoids. Here is the Biot-Savart law, the BS law, as it's affectionately known. And our version of that was a little, or my version, I guess, was a little different from the books. Instead of using mu naught over 4 pi, I am using k over c squared. And then instead of using dl, I am using ds. I am going to make the outrageous claim that the version I'm using is easier. Let me see if I can find that quickly. There it is. So this is my personal favorite version of the, I guess it's here, of the Biot-Savart law. So working in terms of sine theta is here, ds is here, r squared is here. Let's see how that compares. Now, what they've written into the Biot-Savart law version that the textbook is using, what they've done is they've left the dl as a vector, or the ds. I have factored out ds as a non-vector and left the vector as a unit vector. So this becomes a cross product of unit vectors, which for me helps. Anyway, take a look at those comparisons and take a look at applying those to some of the examples. And then the other item that we want to talk about here is ferromagnetism means that we can make actually strong permanent magnets. So iron by itself, iron can be manufactured in a way where when we put it in a strong magnetic field, the iron takes on a permanent effect from that magnetic field, and it takes some doing to undo that magnetic field. So something else to keep in mind is this ferromagnetic effect in the chapter. All right, that takes us through chapter 28. So 27 was magnetic forces, 28 was determining magnetic fields, and we will continue to see examples of doing both sorts of calculations as we move into the next chapters. Now that we've completed chapter 28, we've got a midterm that's going to be based on chapter 26, let me go back, chapters 25, 26 are chapters on currents, and then 27 and 28, magnetic forces and fields, and we'll have a midterm exam once we're, you can take a look at the schedule, take a look at the course schedule, and see when that's going to be happening. Depending on when you're viewing this, it could be tomorrow morning if you're packing this all in the night before the midterm. I'm hoping it's at least a week before it's time to actually take the midterm. All right, I will close that up. So we're through the two magnetic field chapters, and we're headed into that midterm. Good luck with the midterm.